Embedded Solutions at ARM, based in Cambridge, UK. Prior to that, you worked in ARM's enterprise marketing team responsible for the technical community of ARM's internal and external events. For the previous 15 years, he was responsible for ARM's customer training group, delivering over 2,500 training courses to customers and users all over the world, and he has personally trained on every continent except Antarctica, and is a regular speaker at the conference. So the title of Mr. Short Talk is Think Local, How to Migrate Intelligence from Cloud to Devices at the Edge. Please, the word's yours.
Thank you very much for that introduction, and thank you to Gareth for a talk that I could almost have given with the same slides. There's a lot of very, very common subjects that you touched on, so thank you for that. So welcome to what I would think local, looking at the reasons for migrating intelligence to the edge, and the challenges that that poses, and some of the technology that's available on the market to achieve it. As in the introduction, my name is Chris Shaw. My business card says Director of Embedded Solutions in the IoT and Automotive Group at ARM. Basically, that means I'm responsible for helping customers and users and technology developers to put together viable solutions for their technical needs and their commercial needs, either using ARM IP or third-party IP or standard components. It doesn't really matter. I'm interested in getting people to market. I'm based in Cambridge in the UK, and as you've just been told, I ran ARM's technical training group for over 15 years, and that allowed me to travel the world and see what interesting things people are doing, not just with ARM technology, but across the whole world of computing, and it's fantastic. It's a real privilege to be able to continue to do that. The story of ARM, and I've seen a lot of it, I've been with ARM for 19 years and out of university for a lot longer than that, but the story of ARM kind of illustrates and the growth and the change in computing over probably about the last 30 years. And we've seen computing move through a lot of stages in that time, some of which Gareth touched on. 30 years ago, compute workstations were special and unusual, and there weren't very many of them. Your company might have had one, your school might have had one, if you were lucky you might have had one on your desk, and if you were really go ahead, you might have had a small one at home. There are a small number of powerful machines shared amongst many people. And then you get personal computing, where we all have a computer on our desks. Many of us have one at home. I used to avoid having one at home. After spending all day with one, the last thing I wanted to do was go home and play with one. That was a no-no. And then the era of mobile computing, where each one of us has in our pocket a compute device that's more powerful than almost anything of even 10 years ago. And then connected computing, where all these devices that we carry around are connected together and connected into what Gareth very helpfully called systems of systems. Nothing is in isolation, and information and functionality and services are a shared thing across this system of systems. And from only a relatively small number of computers 30 years ago, we now live in a world where computing is literally everywhere. And increasingly, all these compute devices derive their value from the fact that they are connected into a network of much bigger intelligent systems. And we keep being told that the commercial possibilities of this are endless, but scaling that, especially in the embedded world, is becoming a problem. ARM Silicon Partners, for instance, as you can see from that amazing hockey stick graph there, ARM Silicon Partners have shipped over 100 billion devices based on our technology since we started in 1990. And 50 billion of those have come in the last 4 years. And we expect 100 billion in the next 4 years. And that's just ARM. There are other players in the market doing other things. That's just ARM. And most of that growth is going to come in what we call today the Internet of Things. And those devices derive their value from being connected to something central, into something bigger than themselves. And through that connection, through that interaction, they provide a service to users and suppliers. And it's those connections that are coming under increasing stress. Because currently the assumption is that the intelligence is in the cloud, at the centre, out there somewhere. And that has an advantage of concentrating all the data in one place. But it does come with some significant problems, and those are growing problems, because fundamentally it means we have to spend time, energy and money transmitting all that data from the edge to the center where we analyze it, and then we transmit analysis and actions back out to the edge. So if you like, we now have this with the path going all the way to the center. And transmitting all that data to the cloud for processing and then returning actions to the edge just takes too long. It costs too much, it compromises privacy, it uses power, and fundamentally it doesn't scale. I found a few weeks ago, there's a quotation from the founder of an IoT startup, which I really like. He said, "We like to say the cloud is a way to scale AI. But to me, the cloud is a roadblock to AI because there is no cloud that can digest that much data." So this model is not scaling. Much better, for instance, to build intelligence into the gateway, or maybe into the device at the edge itself. That reduces latency, it improves privacy, it improves security, reduces bandwidth, reduces costs, and so on. Then actually the data which you do send to the server becomes more useful. It becomes more valuable to the service provider because it's a digest. It contains only the interesting bits, or the bits that the edge can't deal with. And then it can be aggregated and analysed and transformed into much more real business value. So, moving intelligence to the edge offers a lot of benefits, principally in scaling, but other things as well. It offers the possibility of increasing local autonomy, increasing security, privacy and safety. It also allows us to reduce energy consumption, reduce latency and reduce bandwidth in the network. There are significant benefits, and as a solution it scales to large numbers and large networks much, much better. So I'm going to introduce you to a new principle. It's in the title of the talk: think local. Do the thinking at the edge wherever you can rather than at the center. But we still have to work within those constraints that apply at the edge of the system. Those devices typically need to be energy efficient, cost effective, battery powered very often, physically small, constrained in all kinds of ways. That's the market in which ARM has traditionally operated, and much of our technology directly addresses those constraints, building powerful, intelligent, efficient edge devices. Now, we don't have time today to talk about all of those potential technologies in detail, so I'm going to focus on just three: security, DSP and machine learning. All are becoming increasingly important. And while ARM is not the only provider of technology in this area, it is the one that I know best. So forgive me for using ARM examples where appropriate. So a little context. A typical embedded device that you can see in the middle there takes input from its environment, it actuates some control output. And within the SoC, you'll have key IP blocks and functional blocks, I/O, analog interfaces, memory for code, memory for data, and a CPU to do some compute. And key design criteria would be things like, do we have enough of the right compute capability? Is the device power efficient? Do we have the right support in terms of software, software IP, RTOS, middleware, development tools, and so on? And does it implement an appropriate level of security? Even if you never connect that device to an external system, security is still often a critical component to protect integrity and confidentiality of the data and allow you to trust what this thing actually does and to control its life cycle. It may offer protection to the manufacturer and supply chain, allows you to validate the authenticity of the device and ensure it's not counterfeit or cloned or been taken over by someone else. And connecting a device to an external system adds a whole new level of complexity, and it affects those design criteria in lots and lots and lots of ways. So here we've got a very similar device. It's now connected securely to some cloud to enable it to provide some IoT service of some kind. And the cloud has to be able to trust the device, and that takes your security requirement up several levels. The service is going to be enabled by software running on the device and in the cloud. So processing captured data locally and then sending information about interesting events or interesting situations up to the cloud where you can turn that into long-term value. An IoT device has to be manageable. It needs to be provisioned when it first connects. It needs to be authenticated when it communicates. You need to be able to control the life cycle of updates, especially security patches, and you need to securely terminate its operation at the end of its life. And the physical connectivity needs suitable transport layer security, so you can ensure that private data is kept private and avoid people intercepting your communications. So security requirements touch almost every part of that design, including identity, connectivity, and lifecycle management. So it makes sense to look at security first. And we'll look at how the technology available provides foundations on which you can build a secure solution. ARM introduced about a year and a half ago something called the Platform Security Architecture, and we've tried to make as much noise about it as possible, so I'm hoping you've heard about it. The PSA is an open methodology. It's architecture agnostic, and it's used for analysing threats, architecting secure designs, and implementing secure solutions. And those three steps are very crucial. In particular, the analysis stage is very important. Not all security solutions are applicable to all situations. If your device is not physically accessible, for instance, then you don't need necessarily to secure it against physical security threats. In other situations, they may be absolutely vital, such as bank cards and so on. In all cases, the security solution you adopt has to be appropriate and proportionate to the threats that you identify. And that analysis stage, where you identify and quantify and characterize the threats that you know you're going to face, is absolutely crucial to carry through the rest of the design. And PSA, as you can see, talks about four major kinds of threats. There's physical threats, invasive and non-invasive, software attacks, buffer overflows, interrupts, malware, and so on, communication threats, such as man-in-the-middles, weak random number generators, cryptographic failures, code vulnerability, and then lifecycle threats, things like code downgrade or ownership change or cloning or overproduction or attack through debug and so on. And as you can see on the right-hand side, you need a combination of hardware and software technology to address those areas. In the ARM world, technologies like TrustZone help to protect you against software threats. Hardware IP like CryptoCell helps protect against communication threats. Secure Core and Crypto Island help protect against physical attacks. And you can find more details about those online if you want to go and look at them. And increasingly, for many vendors, template systems are becoming available to speed the development of those secure systems. ARM, for instance, makes available a range called Corestone Secure Foundation Systems. And it's a range of system templates that allow for constrained, mainstream and rich embedded designs based around microcontrollers at the constrained end, multiple processors in the mainstream end, and then rich designs running Linux on a high-performance processor at the top end. And the accompanying software packages, they include security, real-time operating systems, firmware, and so on. And using or picking up a design like that and using it as a reference or a template as a starting point can really reduce your design time, get your product to market much more quickly, and allow you to have much greater confidence that you've ticked those security boxes. Much of the intelligent behaviour that we need to implement relies on having access to optimised software libraries, particularly for functions like DSP and neural network acceleration. Those two are very, very closely related. They rely on a lot of the same underlying maths. So let's have a look at what's available in that from ARM and ecosystem and partners. So much of it, in one sense, all processors are perfectly capable of executing any and all DSP algorithms, just that some of them, as you would expect, are rather much better at it than others. For ARM processors, for instance, you can see an indication of the range of performance points from that chart. Cortex-M4, for instance, that's a very capable core, has a number of DSP extension instructions that improve performance considerably. Cortex-M33 improves about 10% on that from having a cleaner, nicer design. Cortex-M7 is much higher performance beast indeed. That's 50 to 75% improvement. And if you go to something like a Cortex-A32, then there's 200 to 400% improvement. Lots and lots of performance points. Choose the one that's right for you. But extracting maximum performance for complex algorithms like this, let's face it, not all of us understand the nuts and bolts of DSP stuff. This is tricky. This is PhD material, a lot of it, and some of it way, way beyond PhDs. But we all understand, in many ways, what we need to achieve using it. So it's very handy to have optimized libraries, for instance, available. Cortex-M, for instance, we make available a library called CMSys DSP. It's hand optimized by our own experts, many of whom I know, and they're all quite sane, honest. It's open source, it's free. You can download it from our websites, complete with source code, and use it in your products. And there are many other alternatives and analog libraries available to that. You can tailor it to your requirements if you need. It's a very low-level library. Provides implementations of a lot of common building blocks out of which you can assemble high-level DSP functions. And if CMSys DSP doesn't provide what you need, or it isn't high-level enough, then there's an awful large number of ecosystem partners providing all kinds of specialist software for things like image processing, sensor fusion, motor control, and a lot of specialist applications. And that ecosystem is growing very fast and expanding into new areas. And Cortex-A processors offer significantly higher computational performance, and a lot of that comes from the fact they have an extra instruction set called Neon. It's a powerful, versatile vector processing instruction set with a dedicated register bank. And if you were following the press, last week we announced a very similar technology called Helium for the Cortex-M space that you'll see coming into the market in the next year or two. Technologies like Neon and Helium are well supported by compilers from ARM and from other vendors, and there's a large range of open source, in many cases, libraries and solutions which you can leverage these technologies to great effect. A lot of that is open source and very readily available. And finally, because we have to, we talk about machine learning. It's an area of huge interest. Almost every customer I talk to and my colleagues talk to is saying, how do I get ML into my system? My customers tell me I need ML. How do I do that? What is this ML thing anyway? There's a huge interest, and for many people it's a tick box item. I have to be able to say I've got ML in my chip. But it does have real applications, and nowhere is that interest more intense, if you like, than in the drive to push it out to the edge, onto constrained devices, the kind of devices, say, that we find at the edge of the network. For traditionally, we've seen ML as something that happens on big machines, on big iron, in windowless buildings that containing large racks of server material that have limitless performance and bucket loads of storage. Now, if you want to do that kind of thing at the edge, and I believe we do need to do that, then you need to think about it a little bit differently. So, first of all, ask yourself what might be the killer app for ML. I think it's better to turn that question round and actually ask what application will not be affected or could not be approved or could not be extended by adding some element of machine learning. Because machine learning is, like it or not, taking place literally everywhere. Interesting to note, by the way, that over 95% of AI-enabled devices in the world today are in mobile, smart home, and IoT. The remaining 5% of devices are in the server infrastructure centres. Now, from that data, interestingly, and rather pleasingly for me, you might conclude that actually 90% of the AI-enabled devices being shipped today are based on ARM architecture IP, which I find quite nice. But ARM has a breadth of hardware and software IP, and coupled with what you can find out in the partner ecosystem and out on the exhibition floor, which is here this week, you can find technologies to address all of these market segments, from very tiny constrained edge devices whose sole job is maybe to detect you saying, "Hey Alexa." That's his only job, right up to serious accelerated applications running in the data center. And there's a huge continuum in between, being driven very heavily towards the top end by work in autonomous driving. That is driving, pun not intended, far more research and effort than you can possibly believe. I say my group is the IoT and automotive group, and my automotive colleagues are busy building as much ML capability into the technology as they possibly can. They know it's absolutely vital example. And then things like voice and image recognition, natural language processing, that happens very much at the boundary these days between the edge and the cloud. What you've had over the last few years, say, is edge devices that can pretty much recognise you saying, "Hey Alexa," and not much more. And after that, they flip the record button and stream it to the cloud because they can't do anything locally with the audio stream that's coming in. But what we're seeing now is actually edge devices becoming capable enough to move that speech recognition and language processing from the cloud to the edge and do the interpretation and the action at the edge. Now, how much more private is that? Much more. How much more secure is it? Much more. How much less bandwidth does it need? And so on. It's a much, much more scalable solution. It's becoming possible as the capability of devices on that spectrum moves up at the edge. Now, there isn't one way to do machine learning. There are loads of different combinations of hardware and software IP that can achieve the same results with kind of different trade-offs. If we've got, say, always on, always aware devices, very, very power efficient, all the way up to data centers connected to their own powered, nuclear reactor. The ARM ML architecture scales, along with others, to meet that changing use case need. It scales from sort of 2 gigaops at the bottom up to 150 teraops at the top, which is an incredible spread of technology. ARM IP also supports different blends of compute capability for ML applications. So the standard Cortex processors, even from Cortex-M processors. If you go and look at our booth, you'll find demonstrations of image recognition running on a microcontroller, very, very capably indeed. And if you go look at some of the booths of some of our partners, NXP is one I'm aware of, they have a very nice demonstration of voice recognition, again, running on a microcontroller, very, very nice indeed. And there's lots of other ones you can see as you walk around. And then as you move up through machine learning accelerators, specialist image signal processing and object detection capability, and having that set sort of menu of options to choose from is absolutely crucial to enable designers to balance intelligent capability against constraints of cost, power consumption, and so on. And you can combine all of these architectures in lots and lots of different possible heterogeneous systems. Like Gareth, I believe heterogeneous systems are the future, systems that can combine an always-on power-efficient element with a high-performance compute element and make those work in a heterogeneous system are definitely the way of the future. All of that benefits from very, very extensive software support from the ecosystem, from partners, from third parties, and much of it from ARM. Specialist neural network frameworks, something called the ARM Compute Library, which is an acceleration library for compute operations. ARM Neural Network, which is a neural network software framework. It's essentially a unified API that provides you with a bridge to whatever you've got underneath, whether it's a standard CPU, a GPU, an ML accelerator, or a TensorFlow chip, whatever, a unified API onto the same underlying hardware. So here's an example, for instance, of a system which you can build relatively easy using technology which is very easy to get hold of today, that brings vision capability into a rich embedded device. You've got Cortex-M processors, providing sort of always-on capability. You've got Cortex-A processors for heavyweight processing. You've got dedicated image processing and machine learning accelerators when you need them. And the elements of the software stack that you need to put on that are very easy to find, either from ARM, from partners from the ecosystem, or third-party providers. And in the bottom right-hand corner down there, just a quick mention for ARM security IP. Very easy to integrate into the system. There are lots of other solutions out there which mirror the functionality of these two. Crypto Island is a physically secure enclave that allows you to store identity information, software information, and critical user data. And then the Keegan underlying system, which is an embedded SIM subsystem that provides secure identity management. So there are lots of other solutions there, but those are the ones which ARM particularly offers. So, I'm going to get warned in a minute to wrap up. So here we go. Over this presentation, so we've looked at just 3 key technologies to enable migration of intelligence into constrained edge devices. And I think you need elements of all of these in almost all interesting devices these days. If we had time, we could have talked about investments in functional safety, which is becoming hugely important as the IoT extends out into things like autonomous driving, medical devices, and so on. And Gareth talked about the the need to protect the world from the system, and that's what functional safety is all about. We could have looked at the way that technology scales from the smallest requirements up to the most demanding systems across a whole range of possible architectures, and we could have looked at how to build heterogeneous systems that incorporate virtualization and distributed security and distributed safety enclaves and real-time enclaves and so on, increasingly important in intelligent driving. And all it's possible to build all of those capabilities all into the same single physical device using the right combination of IP. So, from my point of view, the ARM architecture really does provide that kind of total compute solution, the edge intelligence that the IoT needs to be secure, to be scalable, to be safe, and to be successful. And just a moment, actually, about the power of open source. Increasingly popular in the IoT space, where we deal with lots and lots and lots of constraints, principally one of cost. ARM and open source are often wrongly seen as incompatible partners, and really nothing's further from the truth. I've been involved with ARM, as I say, for a number of years, and ARM's pretty much always been involved in open source software. And the innovation that enables is absolutely essential to the success of the ecosystem and all of our customers. It now enables pretty much every market segment in which we all operate, from sensors all the way down, all the way up to servers, and all of the intelligence in between. And ARM, just out of interest, actually actively participates in well over 200 open source projects. We have between 300 and 500 engineers across the company actively involved in open source work. And if you combine ARM and Linaro, very close partners, actually as a combination, we are in the top 3 contributors to the Linux kernel, believe it or not, and to the Zephyr effort as well. And we invest very heavily in that, and we're very committed to it, because it ensures embedded developers have ready-to-run software available on ARM from whatever source they choose to get it. And in the RTOS space, so we actively contribute to Zephyr, FreeRTOS and Embed. Not all of those products are from ARM, only one of them is, Embed. The other 2 are very much open source efforts, and we see it as vital to contribute to those. So, looking for a solution from ARM is very much much more than a CPU. You're choosing an IPU from a trusted partner, you're engaging with someone whose success is very much bound up with yours, and you're getting access to support and services and connecting to a huge ecosystem. So thank you for your attention. I think I've just about finished on time. If you want to hear more about some of these subjects, look through the conference program. There are 4 sessions from some of my colleagues tomorrow which build on some of this and follow on from it. But otherwise, thank you very much for your attention. I'm going to guess we're going to take questions offline, but I'm going to be here for the rest of the session and also at the end. So yeah, please do come to me with questions. I'll be more than happy to answer them. Thank you very much.
Thanks a lot for because we didn't have time for any question. So if you have questions, you may ask the speaker after the session, or you may visit actually the education section. Thanks a lot. I think that our next speaker is already there. So.